Welcome to Peaks to Power, a podcast brought to you by the National Laboratory of the Rockies. It's Wednesday, August 26th. I'm Jackson Fletcher.
And I'm Taylor Mankel. Jackson, great intro, and welcome to the podcast.
Thanks, Taylor. I'm excited to be here.
Folks, alongside Karen, Natalie, and myself, Jackson here is going to be our newest host to join the podcast. Tell the audience a little bit about yourself, Jackson. Give us a quick intro.
Sure. I worked at the laboratory as a communications professional since the summer of 2023. I grew up primarily in Atlanta, Georgia, and Omaha, Nebraska, and then I got my degree from the University of Missouri in journalism.
Oh, right on. M-I-Z.
I'll ZOU, Taylor.
Well, thanks, Jackson. For your first episode, we've got a full plate of updates talking about chirality-induced spin selectivity and how the laboratory fared in this year's Oscars of Innovation, or as we know them more commonly, the R&D 100 Awards.
Ooh, chirality-induced spin selectivity. Say that 3 times fast.
Don't you worry, we've got acronyms to come.
You gotta love acronyms. Well, let's get into it. When it comes to basic energy sciences, our work doesn't go viral. It goes chiral.
That's right. We're talking about chirality-induced spin selectivity, CIS or CISS for short.
There's that acronym. Researchers recently confirmed that CISS could be used to help control what chemicals are produced during the carbon dioxide reduction reaction.
Or CO2RR.
Ooh, we're up to 2 acronyms so far. You sticking with us, folks? I think we've got a few more coming up, too. So, the CO2RR reaction is behind the conversion of carbon dioxide, CO2, into other valuable chemicals.
It basically allows us to create pretty useful materials for today's world, literally from air.
The electrochemical conversion of CO2 generates molecules like carbon monoxide, formate, formic acid, and methanol, which are chemicals that constitute fuels and plastics and other materials that we use every day.
Copper is commonly used as a catalyst for this reaction, mostly because it can create ample carbon products. But the CO2 reduction reaction's efficiency is currently limited because of a side reaction that happens, an overabundance of hydrogen, which is not something we want.
Right. We want the formate, the methanol, the starter kits for plastics and fuels.
So back to the word chiral. It's a fundamental property of nature. Think of shapes like spirals or hands. There's always a left and a right-handed version that are mirror images.
Right. If you put your left hand on top of your right hand, they're not the same.
Exactly. A structure is chiral if its mirror image can't line up to fit exactly over it.
NLR's photochemistry researchers found that spiral-shaped chiral copper electrode films in this reaction can suppress the formation of that hydrogen byproduct and improve production of carbon products we're trying to create.
When they used electrodes without the chiral structure, they didn't achieve the same results, which tells us the key for success is for the copper catalyst to be chiral.
The researchers wanted to prove that the results were related to how chiral structures control electronic spin during catalysis. So, they developed a tool called transient Kerr ellipticity.
This tool showed that electrons align their spins or magnetic moments in the same direction when passing through the chiral structures.
2 opposite spins are needed to form a hydrogen molecule, but with CISS, the spins have the same orientation at the surface, so this inhibits hydrogen formation.
And at the same time, that chiral-caused spin alignment encourages more formate and carbon monoxide production, those useful materials for fuels and plastics we use every day.
The researchers are hopeful that this could apply to other reactions besides CO2RR that struggle with too much hydrogen formation.
Exactly. Too much hydrogen in your reaction? Just go chiral.
It's a good one, Taylor.
Now, Jackson, you're new to the podcast team, but you're not new to the lab's award-winning research.
That's right, Taylor. I've been here for 3 years, so enough time to see some groundbreaking research get shared. It's always a particularly exciting time of year because we're in award season.
Now, outside the science world, you may hear award season and think, aren't the Oscars in February? But here at the lab, our Oscars happen in late summer with the R&D 100 Awards.
Given annually by R&D World Magazine, The R&D 100 Awards honor the 100 most innovative technologies of the past year and are chosen by an independent panel of judges.
And this year, NLR took home 4 of those awards.
What do you think, Taylor? Should we give a quick breakdown of each of those projects?
Love it. Let's switch off. Go for it.
I'll go ahead and take the first award-winning technology, which was, drumroll please, Altrios, Advanced Locomotive Technology and Rail Infrastructure Optimization System. Altrios is the first validated open-source digital twin for the freight rail system. It creates unified, integrated simulations of train components, locomotives, fleets, rail networks, and freight terminals, plus the energy use and cost over decades to help de-risk deployments of new tech.
Next up, we have Enduring, or economic long-duration energy storage by using low-cost, particle-based thermal energy storage. This patented system can decrease energy costs by storing energy generated during off-peak hours to use during periods of high energy demand. This uses sand as a storage medium. It's inexpensive, stable, and abundant. Enduring has the potential to provide large-scale energy storage for a capital cost of, get this, less than $10 per kilowatt hour of heat stored, and it can safely store the equivalent of up to hundreds of megawatts of electricity for up to 100 hours.
Okay, next up, Pele. Not the Hawaiian goddess or the famous soccer player, but the suite of exascale reacting flow codes that simulates turbulent reacting flows critical to transportation, electricity generation, manufacturing, and national security. Turbulent reacting flows are everywhere. Almost every flame lit by humans is a turbulent reacting flow, from the first campfire to internal combustion engines that power many vehicles, to the rocket motors that carried Artemis II to the moon. Turbulent flow simulations require simultaneously solving the closely coupled equations for fluid motion, chemical reaction rates, and the release and movement of energy. The Pele suite of codes allows researchers to solve millions of computations simultaneously using the world's most powerful supercomputers to better understand the behavior of fuel combustion.
And finally, perforated membranes for the efficient conversion of carbon dioxide and carbon monoxide to organic compounds. This is the first commercially viable electrochemical carbon dioxide conversion system, and it transforms waste gases into high-value chemicals using electricity. It can cut production costs by as much as 62%.
This award, as well as Altrios, was recognized in the Corporate Social Responsibility category of R&D 100, and Enduring was recognized in the Market Disruptor category.
NLR was also recognized as a contributor to an award-winning technology led by our friends at Oak Ridge National Laboratory called thermophilic one-pot bioconversion of PET waste into value-added aromatics, a bioconversion process turning plastic waste into valuable chemicals.
Including this year's winners, the lab has received 80 R&D 100 awards since our first in 1982.
I'd say that's worthy of a tux and a red carpet. Winning teams will celebrate at the R&D 100 Gala event later this year. And that's a wrap on your first episode. You're officially a Peaks to Power podcast host, Jackson.
Well, time flies when you're having fun.
Absolutely. Now, listeners, we always love hearing from you too. Drop us a note at podcasts@nlr.gov or leave us a review on your favorite streaming app.
Thanks for joining us. The podcast will be back in 2 weeks with more news from the lab. This episode was adapted from National Laboratory of the Rockies news articles from August 2026, written by Justin Daugherty, Sarah Havig, Hannah Hallisker, and Isabel McCann. Our theme music is written and performed by Ted Vodka, and episode music by Chuck Kernick, Jim Riley, and Mark Sanseverino of Drift BC. This podcast is produced by the National Laboratory of the Rockies Communications Office.